Imagine walking out onto your front porch to get the newspaper one morning and getting the shock of your life. After looking over at your neighbor, Sam, who's sitting and reading his own copy over a cup of coffee, you notice a robot carrying a package down the street. Astounded, you observe that after it drops off the parcel on someone's doorstep and walks away, several more robots appear, marching along, performing the same task. So, after rubbing your eyes in disbelief, you whisper shout to your friend, "Hey Sam, where did all these robots come from? Who do you think made them?" To which he glances at you over the top of his glasses with a slightly bored look and says, "Well, I don't think anyone made them. I think they made themselves." Now, does this scenario have any correlation to a situation we could relate to in real life? Well, yes, it does. Our neighbor Sam is analogous to the materialistic worldview being taught today through the state-run education and media platforms throughout the West. The story of evolution, presented as science and fact. This materialistic ideology explains everything through a naturalistic lens, no matter how intricate, complex, or marvelously engineered something appears to be. The foregone conclusion, always trotted out, is that whatever is being discussed was somehow produced by nature, with no appeal to design allowed, i.e., everything makes itself. Now, the robots referred to in our story are represented by the incredible motor protein, Kinesin, that's found inside the cells of all living things. And as amazing as it sounds, they're very much like tiny biological robots walking around inside all your cells at this very moment. And most of you likely never even knew that was happening before now. To understand the world in which Kinesin operate, imagine the scenario depicted in Isaac Asimov's classic 1966 sci-fi film, Fantastic Voyage. In it, a group of scientists were shrunk in a submarine and injected inside someone's body to perform microsurgery on him before reverting to normal size. Now, of course, we haven't been able to shrink ourselves yet, but advances in biochemistry have allowed us to take many fantastic voyages inside cells through the use of electron microscopes. And what we've discovered through them is truly fantastic. Electron microscopy is a technique for obtaining high-resolution images of biological specimens by using a beam of accelerated electrons as a source of illumination. And what's discovered inside the simplest of living things is astounding indeed. As PhD geneticist Michael Denton described, to grasp the reality of life as it has been revealed by molecular biology, we must magnify a cell 1,000 million times until it's 20 kilometers in diameter and resembles a giant airship large enough to cover a great city like London or New York. What we would then see would be an object of unparalleled complexity and adaptive design. On the surface of the cell, we would see millions of openings like the portholes of a vast spaceship, opening and closing to allow a continual stream of materials to flow in and out. If we were to enter one of these openings, we would find ourselves in a world of supreme technology and bewildering complexity. Now, part of that bewildering complexity is our topic of conversation, kinesin. Kinesin proteins aren't living things. Rather, they're a family of miniature motor proteins inside living things that transport cargo around inside cells and are remarkably humanoid in appearance. Having two legs that allow them to walk along roadways inside cells and two arms that allow them to carry packages full of important cargo, they're like the postal delivery people, but on a mind-bogglingly microscopic scale. At only 7 billionths of a meter long, they consist of, utilize, and synchronize with an incredibly complex array of microbiotechnology that rivals the most sophisticated feats of engineering that humans have ever achieved. Now, there are many different types of kinesin and kinesin-related proteins, each with different specifications and functions that have been discovered in various organisms from yeast to humans. But the following example is a very basic scientific description of what a typical kinesin does and why it does it. Inside life forms, proteins and other needed parts must be delivered to specific places within the cell at precise times. Now, if the needed part is a protein, for example, a manufacturing plant, called a ribosome, receives blueprints for the part from the nucleus. The information is stored in the nucleus on a strand of DNA, but the blueprint is sent in the form of an RNA copy of that section of the DNA. Now, this is obviously a complex coordinated effort, as something must first access the creature's DNA library, unzip it at the exact location needed to copy the specific information required for whatever part is to be manufactured, create a copy of the information for the part, and deliver it to the factory. Afterwards, another organelle in the cell, called the Golgi apparatus, packages the needed part and wraps it in a bag called a vesicle, then imprints the address where the part is to be delivered onto the outside of the parcel. Then a kinesin is summoned, and as mentioned, a typical kinesin has two arms on one end holding the cargo, the vesicle, and two legs on the other end that walk along the roadway called a microtubule. So it picks up the parcel and walks along microtubules in the cell and delivers the parcel where it's needed. Now, if that sounded like a lot of technobabble to you, let's use a more relatable scenario that, although sophisticated, actually pales in comparison to what kinesin regularly do, so that we can better understand the level of complexity at which these micromachines interact and operate among the other systems inside cells. Now, imagine a fellow named Joe is working at his job one day when suddenly the machine he's operating breaks down. After doing a diagnostic to determine what happened, he identifies a broken part and makes a call from a cell phone to a local manufacturer in his contact list, requesting the needed component and giving them the part number. The manufacturer takes the order and records Joe's address. However, although they have a list of all the part numbers on hand, they don't have the schematic required to manufacture it. So they send an email to another company that has the copy of all the blueprints for every part needed in the industry, requesting the needed diagram. So someone there makes a photocopy of the needed section from the master database and delivers it back to the manufacturer. And now, having the instructions to construct Joe's needed part, the factory then constructs it, puts it in a package, marks it with the postal address from its database, and calls a courier company to send a delivery person. After arriving at the factory and acquiring the package, the courier punches in the GPS coordinates and travels along the route plotted to deliver the package to the proper address so that Joe can get on with his day. And voila, mission accomplished. Now, most would agree that the level of complexity, both in the engineering and manufacturing prowess combined with the multi-tiered levels of coordinated communication and interaction that I just described in my analogy, is pretty impressive. Not simply the technology, the communication systems, or the manufacturing capability and the databases combining these integrated components, but also the specialized knowledge required at each step along the way. Beginning with Joe performing the troubleshooting analysis of his broken machine, all the way to the admin person's insight about which area of the metadatabase to access. Truly, such intricately synchronized problem solving would be considered close to peak level human sophistication. And of course, in our example, all of these steps were coordinated by intelligent people at every stage. Well, as impressive as that may have been, let's understand that the actual processes involving kinesin are far more impressive than what Joe experienced. And all of the programming involved was, according to advocates of the story of evolution, supposed to have been generated via random mechanistic processes over millions of years, all without any intelligence behind it. However, just think about the implications we've gone over here. The fact that cells are somehow able to know when and where a specific part is needed inside of themselves requires an incredibly sophisticated diagnostic system. It also requires a database of all of the parts that may be stored and the ability to access them at the appropriate times when the correct, specific communication is activated through the system. That communication then must trigger the access of a blueprint for the needed part and the assembly and packaging of it, along with the recording of some type of address for the kinesin to access and utilize in order to travel to the correct destination. Just as an address is useless to us without some sort of map or GPS system of the location. However, the more we discover, the more mind-blowing it gets. Just the kinesin proteins themselves function with incredible efficiency. A kinesin's motor produces nearly 15 times more power than most man-made engines and is nearly twice as efficient as a gasoline engine. In addition, kinesin are extremely fast, moving at a rate of 100 steps per second. And if we were to somehow scale up a kinesin to my height, it would move approximately 600 meters per second, over 2,000 kilometers per hour. As Stephen M. Block from the Department of Molecular Biology at Princeton University said, scaled up to our own dimensions, a motor with corresponding properties would travel at similar speeds and produce as much horsepower per unit weight as the jet engines of the thrust supersonic car, which recently broke the sound barrier. Incredibly, kinesin also have what would be considered a bypass mode ability that allows them to navigate around obstructions that they might encounter while delivering packages. And similar to how a GPS system recomputing mode will calculate an alternate route should obstructions arise, kinesin have demonstrated the remarkable ability to reroute around obstructions when needed. Of course, this not only demonstrates programming of the kind that computer science describes as conditional statements, illustrated by an if-then-else construct common to most programming languages, i.e., if an obstruction, then reroute. It also means that they can somehow determine alternate routes through some type of program operating in the background that can provide the most efficient path available. And no one yet knows what exactly that program is or how it works. Kinesin proteins also coordinate their efforts should the task at hand be too much for just one of them to complete. Like runners in a relay race, kinesin sometimes hand off their cargo to a fresh worker after bringing it a certain distance. And if the cargo to be transported isn't just a one-man job, so to speak, multiple kinesin will join and pull the load together. And however mundane a simple delivery service may seem, research has shown that kinesin do far more than so-called grunt work. Among their most important functions are the support of cell division and transporting neurotransmitters needed for neurons to communicate with one another. Some kinesin dismantle microtubules, and since controlling microtubule length is vitally important during cell division, as it can cause chromosomal instability, which is linked to human cancer, their work is very important indeed. As one researcher said, if kinesin were to fail altogether, you wouldn't even make it to the embryo stage because your cells wouldn't survive. It's that important. And kinesin are powered by the universal energy compound known as ATP, which is produced by another engineering marvel inside all living things, ATP synthase, the molecular motor. Every molecule of ATP absorbed by kinesin allows it to take a step. And without the ATP synthase motors, there'd be no way for the kinesin robot to function, which adds yet another extraordinary level of complexity to the processes involved. Cells are also extremely efficient, and this is remarkably illustrated by how kinesin have a hibernation feature and enters an auto-inhibited state when not in use. Similar to how modern computers shut down after a period of inactivity, kinesin fold over and enter into a sleep mode when cargo isn't attached to prevent ATP from being wasted. When needed, they reactivate somehow and carry on with whatever new task they've been assigned. There's also good evidence that they're either dismantled and recycled or transported in groups back to the center of the cell by large transport units, much like how buses, streetcars, or subway trains shuttle groups of people around in cities when they're done with their tasks. Now let's just be honest. If any scientist were somehow able to design such incredible microtechnology, they would likely receive the highest possible accolades and be the recipient of the most prestigious awards available from the scientific community. But of course, no scientist has even come close. And yet scientists have minds. Nature doesn't. So unless nature could display the capability to construct such marvels, would it not be more logical to invoke our Creator as the source of these? But in a culture with an education system committed to naturalism, God is never given the glory for such marvelous creations. It's the story of evolution that supposedly explains such nanotechnology. It is impressive how nature manages to combine all of these functions in one molecule. In this respect, it is still far superior to all the efforts of modern nanotechnology and serves as a great example to us all. Of course, naturalists typically appeal to the concept of deep time to explain away such marvelous constructs. The materialist mantra is simple to complex over millions of years, repeated ad nauseum. This is their typical modus operandi for explaining away the incredible complexity continuously being revealed by modern scientific techniques, by declaring that all things, no matter how miraculous they might seem, are possible with enough time. Naturalists brandish the wand of deep time with impunity, waving away all criticisms of the story of evolution that appeal to examples of design. Now, this is a terrible argument, of course. In our experience, even with intelligent input and upkeep, things get worse over time, not better. However, the problem for them in this case is that the more they research, the more they run out of time. Why? Well, originally, kinesin were thought to be only in the cells of organisms with a nucleus, eukaryote cells. But evolutionists' best guesses of when first life, consisting of so-called simple prokaryote cells, appeared on Earth is around 3.8 to 4.3 billion years ago. As evolutionists believed that eukaryote cells evolved well over 2 billion years ago, that meant such incredibly sophisticated constructs as kinesin appeared in life very early on indeed, in less than or just over half of the supposed time life was on Earth. How could such marvels appear so quickly after evolution supposedly began? And if trying to explain that type of sophistication in such a short time wasn't enough of a headache, researchers now propose that types of kinesin must have appeared prior to eukaryotes, in what researchers call the last common eukaryotic ancestor, the LCEA, which means they must have come into existence even earlier on in the deep time framework. As one researcher put it, a large proportion of the extant diversity of the kinesin superfamily was already established before the radiation of eukaryotes from the last known eukaryote ancestor. And now new research has revealed a kinesin type within bacteria, which, according to the story of evolution, evolved 3.5 billion years ago. A eubacterial homologue of a kinesin light chain gene has been isolated and characterized from the cyanobacterium Plectonema boreano. But that would mean complex features like kinesin were here from at least very near the beginning of life, according to their imagined evolutionary timescale. Again, this is biotechnology far superior to anything the most intelligent scientific minds on the planet have ever produced, which is likely why evolutionists have suggested, without any observable evidence, that perhaps these bacteria were simply given this genetic software package at a much later date via lateral gene transfer after it had evolved elsewhere, which of course would include kinesin. The commonly taught evolutionary story that simple life evolved into more complex forms is simply false. True science is based on observation, and what we've observed is that there's no such thing as a simple life form, because even the simplest creatures that we've seen aren't simple at all. What we have observed is life forms that range from mind-blowingly complex to a level of sophistication that's virtually inconceivable in terms of brilliant design and functional ability. Should evolutionists believe that in the past there were simpler life forms that existed other than what we observe today, which are not simple in any true sense of the word? they believe that on faith, not facts. And common sense tells us that when we see robots in factories or communication devices such as smartphones that can connect to the internet, share information through vast and diverse networks, GPS systems that required countless hours of data collecting and utilization through sophisticated state-of-the-art satellite systems, etc., in our everyday life, they're always the result of intelligent design. And yet, as a culture in the West, we've been feeding our children into indoctrination centers for decades now. And these institutions have been teaching young minds, in contradiction to all human experience, that a no-mind process, evolution, can produce far more sophisticated technology than what the most brilliant scientists on the planet have ever achieved, and that somehow matter arranged itself into minds that have determined matter is in fact better at creating constructs than we will ever be. As Jack Szostak, an evolutionist from Harvard Medical School, admitted, "We aren't smart enough to design things. We just let evolution do the hard work, and then we figure out what happened." Now, are we supposed to believe that this is logical, reasonable, or rational to any degree whatsoever? No.